I'm Gavin Clark with the National Museum of Computing and Reading Museum, and we are interviewing former employees and customers of Digital Equipment Corporation as part of the 60th anniversary of DEC Computing opening its first office in the UK. It's December the 7th, 2023, and we are in Bletchley Park at the National Museum of Computing. I'm here talking to Peter Campbell-Burns. Peter, let's start with the basics first of all. Please tell us your full name and your place and year of birth.
My name is Peter Campbell-Burns. I was born in Harrogate, Yorkshire in 1960.
And tell me a little bit about your family background. What did your parents do and what kind of background did you have?
It was quite mixed. My mother's side came out of retail, but my father was an officer in the Australian Air Force at the time that I was born. That is where my interest in science came from. My father was a scientist by profession. He was heavily into aerodynamics. And interestingly was for a while seemed to be a spokesman for the Australian Air Force on space exploration in the 1950s, judging by the number of press cuttings I've got. So there's always been a push towards science from the family side.
And what did you study? Where was your school and what did you study at school?
Well, the sort of formative years would have been my A-level period, which was down in Worthing in West Sussex, and I did chemistry, physics and mathematics. I then went on to study computer science at Manchester University, graduating in 1982.
Tell me a little bit about the computer science degree. Manchester, obviously a huge computing centre. What was you studied computer science at Manchester University? Tell me a little bit about what you studied, and this would have been where you first experienced DEC computers, I understand.
That's right. Manchester's curriculum at that time was quite interesting because Manchester evolved from electronics engineering, and it was heavily involved in development of early computers. For example, the Williamson display tube, which was a form of early storage. So the course at Manchester was quite strongly biased towards the hardware engineering side. So a lot of work around arithmetic logic design, computer design, parallel computers. There was also quite a strong mathematic element to it in the first year. We used a PDP-11 computer to do some basic learning coding, learning assembly language in the Macro 11 assembly language, which was the assembly language for the PDP-11s. And we sort of used that for sort of learning about and exploring sort of operating system fundamentals, so building simple file systems and the coding around that.
This was your first experience of DEC?
It was my first experience with DEC. And actually it was quite, that period was, I didn't realise at the time, was going to have a very strong influence on my career direction. A little bit of an interesting story, but I did actually start off doing accountancy after I graduated because I'd got all of this knowledge of computers but no idea really where I wanted to apply it. So I thought I would go from the business end and I started doing accountancy, but after a few months I realised that really wasn't for me. And I resigned, and on the way home I bought a New Scientist magazine. There was an advert in the back for a position at University College as a programmer analyst. I applied for it, I got an interview. I had the interview in the morning, and what I didn't realise was my boss-to-be lived around the corner where I lived in Archway in London, and by 5 o'clock in the evening there was a hand-delivered letter offering me the job, and it was entirely based on my PDP-11 experience at university.
That's interesting. So what did you qualify? So you got a qualification and you went straight into accountancy rather than into a computer field.
Exactly. Yes.
What was the thinking on that?
Well, it was just that I had knowledge of computing, but I didn't really know where I wanted to apply it. I didn't feel that my direction was necessarily going to be hardware, and I'd had a very hardware biased degree. So what I wanted to do was maybe gain some more business skills and sort of join up the computing with that. But actually, I mean, while I enjoyed the academic side of accountancy, the actual 9 to 5 of audit, just not for me at all. And I learnt a lot about myself in that period.
What do you think it was about the, you said the application process went quite quickly and the DEC experience helped you. How did it help you to get this position?
I think I was the first person that they'd interviewed who had good knowledge of PDP-11s. And I think also my enthusiasm and excitement about science was obviously a motivating factor.
Why was the PDP-11 so important to them and to you?
The department relied heavily on PDP-11s. They were used in data acquisition. The Department of Physics and Astronomy at University College was involved in some really quite high-profile experiments working with CERN, the Centre European for Research Nuclear. The sort of nature of the experiments were to basically explore the fundamentals of matter, elementary particles. The scale of the experiments they were running were breathtaking. So one of the first things that I got involved in was in the digitization of bubble chamber photographs. So a bubble chamber, if you could imagine it like a dustbin full of liquid hydrogen, and you fire a high energy particle beam into that dustbin, and some of these particles will hit the protons within the liquid hydrogen. And at the exact moment they fire the beam, the hydrogen is decompressed, and so the liquid hydrogen boils along the tracks. And 4 photographs are taken from different angles, and those photographs then have to be scanned and digitized to enable things like the energy levels, the momentum, the electric charges and so forth to be calculated. So PDP-11s were used in that digitization process. The 4 images were projected onto a tabletop one at a time, and someone would work with a puck, and they'd actually I'd label the tracks, and then with a puck they'd go around and measure the tracks. And we had 4 of these measuring tables interfaced to one of the PDP-11s. There was also another amazing device called Sweepnik, which used lasers and would automatically follow and digitize the tracks. You just had to give it a head start, and through some very, very clever optics it would follow the tracks. So there was another PDP-11 driving that. Another project I got involved in was to use a holographic bubble chamber. So instead of having to take 4 photographs and then sort of measure the tracks independently and then bring the data together to do sort of 3D reconstruction of coordinates, with the holographic bubble chamber, you just move the photograph left, right, forward and backwards. It's a 3D photograph. So I wrote some data acquisition software for digitizing holographic photographs. Then I had a chance encounter. I'd been to a bookshop near the college. I bought a book on the 68,000 microprocessor, and that was on my desk when a professor came in and said, "Oh, we need somebody with those skills. Are you interested in 68,000? I said yes, and that then got me involved in using prototype or putting prototype detectors into experimental beams at CERN. So I was actually visiting CERN, and I was running the sort of data acquisition on prototype detectors. And a lot of that data, when we got it back to the college, was initially we'd sort of process it on PDP-11 computers. But then the department invested in a DEC VAX computer. We got a DEC VAX 750. So then I started to learn VAX VMS, and that then started a new career trajectory for me, because after I left University College, I joined a defence contractor which used a VAX 780. And the application there was a military command and control system that they were building, Project Bates, and they were using the VAX 780 to run databases that modelled the database that would be in place in the operational system. So effectively, it was an early application of using metadata, data to describe data. I did that for several years. That was an interesting environment because although it was using databases on VAX 780s, they interfaced a Brittonly IDM to the VAX. Now the IDM stands for Intelligent Database Machine. So what this was effectively a processor that was dedicated to running SQL databases. So that gave better performance. After I moved on from there, I joined another consultancy company which had an in-house VAX 780. And because of my VAX experience, I then ended up being system manager of that VAX for a number of years. And then when we relocated, that VAX was retired and the consultancy invested in a micro-VAX to replace it and some VAX stations as well.
So a long career involvement with DEC systems. Tell us, go back briefly to the CERN experience. Why did CERN rely on PDP-11? Why were they using PDP-11s? Other computer systems were available. What did they have that others didn't?
There were a number of other systems around in the university. The department also ran a GEC 4085, which I also used. And in my own sort of career history, I dabbled with things like prime computers and so forth. But why PDP-11s? The PDP-11s were a machine in which it was relatively straightforward to interface external devices. It was used in a lot of laboratory scenarios. It was sort of well used and well understood in that sort of environment. There was already a lot of hardware out there that would allow you to interface equipment to the PDP-11 Unibus architecture.
When you say interface, what does that mean?
So actually sort of to connect an external device to the computer so that it can read or control. So for the measuring tables that I mentioned, we used a system called CAMAC. So you basically had an electronics crate. There would be a Unibus interface module in the CAMAC that you'd connect to the computer. Then you could put in other modules which would allow readout. So for example, for the measuring tables, it was a two-way control. We used the PDP-11 to control the lighting, to move the film rolls forward and backwards, and then also to read the puck position. When the measurer pressed a button, the puck position would be measured, and it would be read into the PDP-11 via CAMAC. So I think it was probably the ease of interfacing.
Why is that difficult? Is that because DEC was just very good at making interfaces, or was everybody else so complicated, or had they become such a standard that everyone was all the people who made the peripherals were just writing to DEC?
You have to go back, I think, and look a bit more about DEC's history. The way that DEC evolved. I mean, I read that in the early days of DEC, when they wanted funding, they avoided using the word computer because at that time it was a bit of a tainted word. But they were very much into sort of laboratory modules and readout and control, and they evolved from that. And I think that legacy probably stuck with DEC and was one of the reasons why the PDP-11 was so successful. I think also another factor would have been cost. I think it was cheaper than many of the alternatives, and it was just such an ideal platform for using in a control scenario.
What do you mean ideal in what way?
The fact that you could buy off-the-shelf things to plug into your PDP-11, such as CAMAC modules, it didn't involve doing a lot of bespoke work. There was already a lot of software and hardware that you could call on. I've no idea what drove CERN in that particular direction, because I wasn't part of the CERN decisions, but certainly the investment that CERN made in for example, supporting software in the DEC environment meant that it was so much easier for the likes of University College.
It's incredible to say that thing, because today computers are so much more plug and play, aren't they? I mean, it's a different world then, isn't it? Much more complicated to get at components.
It's an incredibly different world. If you sort of compare today, I mean, in my house, I've probably got something like 25 Raspberry Pis, and not one of them has less than 64 gigabytes of memory. Now, the programs I was writing on a PDP-11, I had 64K of memory and 64K of address space. And you had to place, well, not only did you have to consider performance and the amount of resources you were using, such as memory, but we had to employ tricks to be able to write the programs we needed. So, for example, the software that drove the measuring tables, there's no way that would fit into 64K bytes of instruction space. So DEC provided the task builder, which allowed you to build an overlay tree. And what the overlay tree did was it just made sure that the subroutines that you'd written in your program would be in memory at the time you needed them. And when you didn't need them, they could kick them out and bring in another subroutine to replace that, one that would be needed. And that way, you only had in memory what you needed at the time, not absolutely the whole program. So it's interesting. I mean, if you ever look at an install on Windows 11 and just look at how many gigabytes of disk space that takes up, I mean, we were using disk packs of only 5 megabytes, and again, you know, working in 64K of address space, the constraints were so different. I think another thing that made that period so exciting was, in a way, it was transitionary, because big mainframes were quite well established. I think the sort of late 60s, 70s was definitely a period of growth in mini computers. So you had companies like for example, Prime, producing smaller, cheaper computers. In going in that direction, it suddenly made computers a degree more accessible. So when I sort of first encountered computers, they were in huge rooms, they were, you know, dedicated staff, you had tape librarians doing everything, and you interacted with that machine solely through a terminal. Once we got into the mini computer domain, well, if I needed to store some data to tape or recover some data to tape, I walked into the room myself, I got tape from the cupboard, I put it on myself, loading disk packs. There was just so much more of it, was just so much, you know, tactile, interactive. You actually got to physically play with it. And that was quite a big change at the time. I mean, today, you know, you've got more computing power in your mobile phone every single day. Even children have more computing power in their hand than you know, the PDP-11s and VAXs that I was using. But it was just such an exciting time. We take so much for granted. And I think to some extent, you know, people have lost touch with the technology.
Let's just focus on, so it's interesting, you mentioned the DEC experience there and the mini computers. The DEC obviously played a large role in that, and you're using PDP-11s. It's enjoyable looking back on it, but how frustrating was it at the time to work with such a tiny amount of space? How much more complicated was your job made by having this stuff, or is that offset by the liberating aspect that DEC had made things so much more usable than having to go into a large computer room?
Well, the question, so the answer to that question is sort of relative, because, you know, I've got a Raspberry Pi with a 128 gigabyte card in it, and in 10 years' time, people might laugh at that and say, how did you manage with such a small amount of space? How did the AI work? At the time, it didn't feel like it was a constraint. At the time, it felt amazing. It felt empowering. And I just think the fact you were working with tight constraints, to some extent, just changed the nature of the problem. Programming is problem solving, it's creativity, it's got so many facets about it, and working around the size constraints was just part of that. You could still do a lot of the same things, you just had to think about it differently. Today, we get, you know, tremendous computer performance because we can do so much more in memory. In the days when I was working with PDP-11s, we were having to write more things to disk, so things ran slower. But you didn't perceive it as running slower. It was, you know, in its day, it was still trailblazing.
And you were working with some big workloads. How big were these projects, the CERN projects? How do you have any sense of how big the workloads were? How much intensity there were in computing space or storage? I mean, how important these were as well?
Well, the PDP-11s at University College were used primarily for data acquisition. So the volumes that they were handling weren't high. Once the data was digitized, it was sent off to IBM mainframes at the Rutherford Laboratory or at CERN for the big number crunching. So those applications, the workloads weren't high. Although the volumes of images that were actually digitized were tremendous. I mean, the measuring tables, usually it was students earning some extra money to support their education. They ran 7 days a week, 4 tables running. They quite often ran through the night. So the volumes of particle interactions that were digitized were tremendous, but on any individual sort of point in time, then the numbers were small. Moving on though, I mean, when I was working on Project Bates, we had a 780 that was being used. Primarily it was a database engine, but it was also used for code development. The code was, I'm trying to think, Coral I think the language was they were using. And there was an interesting performance constraint because what actually happened was there were so many users on the system multitasking at the same time, compiling, running SQL queries, that the system couldn't actually support the load. Performance went through the floor, and the company instigated a 4-day week so they could actually overlap some projects. So people were working a 4-day, 10-day week, every other weekend, a long weekend, and that was just simply to get around the performance constraints.
And that was on the VAX system?
That was on the, yes, that was a VAX 780.
Okay. And do you any sort of the bubble technology at CERN, and do you have any sense of any breakthroughs that did the news filter down of what you were doing? Any sense of achievements they were making or discoveries that were made as a result of using these systems? Well,
there are an awful lot of discoveries came out of those projects. I mean, you can't necessarily say that the discovery was made by University College. I mean, the way it works is that they predict a certain behavior. They should see, for example, out of 1 million particle interactions, if they see a statistically significant number, whatever that is, then that sort of proves what they're trying to find out. Now, the films that were captured from the bubble chambers would be distributed between all of the participating collaborators in a project. So, you know, some might be going to France, some might be staying in Switzerland, some might be going to Germany, and all of that data, so the events that they're looking for could be discovered by many different institutions, but it's when you bring all of that together that you actually, you know, make the discovery. So things like, please don't ask me to explain it, but the W boson, for example, was one of the things that came out of bubble chamber experiments. The curious thing, I mean, I described a bubble chamber as like being a dustbin full of liquid hydrogen, and I think in terms of scale, that's about right. But when you put the magnets and everything else around that, I remember standing on top of BEPS, the big European bubble chamber, and it was bigger than a 3-story house. It was huge. It's an amazing, exciting place to be.
How do you sense how big these images were? You said they were large in capacity.
When I mean the individual negatives would have been probably 2.5 inches square, but when projected onto a measuring table, they were probably at least 1.5 meters, maybe 2 meters square on the table. And very beautiful to look at.
How much data did they generate? Do you know how big they were in terms of megabytes or gigabytes?
I wouldn't know off the top of my head. I mean, some of the images would be quite complex. And the scanners would know what's of interest and what's not of interest, so they wouldn't necessarily scan everything on the table. And I guess, you know, there may be 50, 100 points to each line that they measure, and some images might have a few lines, some images might have 20, 50, depending on how complex the interaction. So each image wasn't a huge amount of data, but it was quite a skillful job to know what to scan and, you know, how to scan it.
It's an interesting observation that this stuff had to be to convert from analog to digital, and the PDP was used to convert it to digital. That obviously wouldn't happen now. That role has kind of been overtaken by history. Those images would be captured digitally straight.
That's right. When I started taking prototype detectors over to CERN, they were building the tunnel for the Large Electron-Positron Collider. Now that tunnel is 27 kilometres in circumference. It's exactly the same tunnel that they've used for the Large Hadron Collider, which has been in the news a lot. And if you look at the detectors for the Large Hadron Colliders, they're entirely digital now. So they, you know, scintillation counters, those basically measure the energy of or detect a passing particle because they generate a flash of light which can be picked up by photomultipliers. They have detectors called drift chambers, so when a particle goes through the chamber, it ionizes some gas, and the ionized atoms drift towards sense wires, and it's the time it takes between detecting that the particle's gone through, which wire it hits, and how long it took to hit that wire. You can work out exactly where the particle went through. They have calorimeters which measure the amount of energy, so that might be, for example, how bright the flash is, and it's all digital now. And the volumes of data are so immense that actually most of the interactions and most of the collisions that the Large Hadron Collider records are thrown away. The data comes in, it goes through effectively a processing tree, and at each level they decide if there's anything interesting, and if at some level they decide there's nothing interesting, the whole thing is thrown away and they wait for the next event. And it's a vast amount of data.
Let's talk a little about because you mentioned the VAX systems you used. You've moved from PDP to VAX. What was that like? How any difference, noticeable difference to you as a user, as a programmer?
Yeah, it was a completely different environment. It was also a transition from being less hands-on. You tended not to interchange disk packs because we had bigger disks. Occasional use of magnetic tape to export data, but you know, gone were the flashing lights, gone were the switches on the front. You sort of didn't feel as intimately connected to the machine. It was a new operating system to learn. On the PDP-11s, I was using RSX11M Plus, and then we had to move over to VMS. Very easy to learn. There was a lot of things in common, but of course, what the VAX did was it broke that constraint of 64K of program space, 64K of memory, because VAX stands for Virtual Address Extension. So what the VAX did was it was one of the early sort of pioneers of virtual memory. So what happens is that you have your active memory, and then you have some secondary memory which will be on disk. And what happens is that the sort of active memory in the computer plus the disk together gives you a wide address space, and it divided the memory up into pages. And if a page wasn't being used, it would be swapped out onto disk. But if another piece of code accessed a page that was swapped out, it would be swapped back into memory. So all of a sudden, you've got a much bigger address space to play with. You could do an awful lot in memory, and you could, your programs would run faster. You could think differently about how you coded. Your big challenge moved more towards what is the problem you're trying to solve, moving away from how do I get a quart into a pint pot. That was quite an interesting transformation.
How do you think DEC did with that transfer? Obviously, compatibility was an important issue because it was no flashing lights, but you recognised that they'd done a good job on that, or do you think there were issues with that?
It was just the nature of computing. I mean, in the old days, if you look at some of the old IBM computers, you have an array of lights and an array of switches, and that was how you controlled the computer, and that is how you knew what was going on in the computer. And the VAX wasn't the first to do this. They had PDP-11s, but basically you can replace all of those switches with another smaller computer that would allow you to interrogate, would allow you to control the computer. So you could actually do it from a console terminal rather than actually having to flick switches and inspect lights. So that was just part of the evolution of computing. From a personal point of view, I just loved the tactile nature of working with PDP-11s. And that started to disappear. I sort of felt that, for me personally, computers became less exciting. Maybe the software became more exciting as time has moved on, because we can do so much with the amazing sort of hardware resources and processors that we have today. But I just love that tactile nature of computers. That really, really excited me in the day. I miss the noise or the scream of the line printers and things like that. It's all gone. In fact, I mean, in the office that I work now, I'm currently a data engineer in an automobile company. We are completely paperless. I don't think there is even a printer in the office at the moment. It's so different.
Tell me a little bit, you come back to this again, this kind of like your love for the experience. And I think in the survey you said you felt you talked about the consistency across platforms. It made you feel a part of something. DEC machines were a real joy to use. They felt ahead of their time. There's a lot of things you've said in that. Consistency across platforms, what did you mean by that? And why was that important?
Even the transition from PDP-11s to VAXs, the early sort of large VAXs, 780, 750, to the micro VAXs, it was never a big jump. It was there was enough familiarity across the range that always sort of, you know, it didn't need a huge amount of adjustment. You could do more things. Yes, things were different, new commands, but it was very consistent. There was consistency in the programming languages. When I was at University College, one of the other machines I used was a GEC 4085, which I think was the OS 4000 operating system, and that was you needed a slightly different mindset. The commands were different, even sort of vendor specific features in the compilers. With DEC, it was consistent. Also felt like you were sort of always on a leading edge. One of the most exciting things in my time at UCL with regard to the DEC platforms was the introduction of DECnet. Now, DECnet was digital's equivalent of Ethernet. It was a bespoke protocol. It's not like the Ethernet that we see today. It was in the early days. Today we have thin Ethernet wires which use twisted pairs. In the days of digital and DECnet, when I was at University College, the Ethernet cable we were rolling out was as thick as your thumb. You could only tap into it and put a transceiver on at certain points. You couldn't just put it anywhere. But for the first time, we started connecting our computers together in a way that would allow high-speed transfer. We weren't running around with paper tapes. I do remember actually before the introduction of DECnet implementing a file transfer protocol that actually connected our GEC 45 and PDP-11 via a 9600 board computer terminal line. So basically it was as if one computer was printing to a terminal and the other computer would think it was reading from a keyboard. Once we had DECnet, we had high-speed file transfer. But this is where we start getting sort of into interesting domain, because DECnet took us down the road of starting to cluster computers. And really this was laying the foundations of what we all sort of accept today with cloud computing. DEC was ahead of its time with that, and that was really exciting to be part of. You also felt you were part of a community. There was a lot of help and support out there. I wasn't a member of it myself, but there was DECUS, the DEC user group. DEC itself was very good at keeping in touch. The quality of their products, the computers, the documentation was absolutely superb. And I also felt quite privileged to have attended a number of training courses that DEC provided, initially from a small office in Reading, but the later courses I did were Shire Hall. So I did basically VAX fundamentals, system management courses, various courses I did at DEC, and everything was done really, really well. Every interaction with the company. It was a bit strange to say, but the technology was such that occasionally chips would fail, and you'd have to call the DEC service engineer. And I always used to look forward to a visit from the service engineers, because you could actually have an interesting chat with them, and you could learn so much from them as well. Things that that wouldn't necessarily be in the manual. It was their knowledge was quite amazing. I mean, one anecdote was I called at DEC and I gave the error that was given, and the diagnostic said that there was a particular failure. I can't remember what it was, and the DEC engineer said, "Oh, ignore that." He says, "When you get that error, it's actually a failure in another board. I'll come over with that other board." He replaced that other board, and wham, everything was fine. The knowledge these guys had was superb.
How was the relationship with with DEC? And obviously, we hear of stories where DEC has this concept of do the right thing. I don't know if you come across that, and do right by the customer. We hear the stories from DEC's perspective. I wonder, as the customer perspective, it seems like you experienced that the support was already there and the literature was already there. Did you have any kind of concept, there was a philosophy driving DEC, to do the right thing, and how did that kind of impact you in your work?
I didn't really get a feel for that or have any awareness, because I wasn't particularly looking out for it at the time. It's just that they were there whenever we needed them. The updates to software and documentation was regular and reliable. It was just a nice thing to be part of.
And how important was that? Because you've had some very, we might say, mission critical roles, some very high performance systems. How important was it to have this?
Well, it's vital. I mean, in terms of the digitisation of the bubble chamber photographs, it was vital that we kept up progress. The volumes of scanning that needed to be done were substantial. If we couldn't meet demand, we might have to return the rolls of films to pass them off to other universities to process. So in terms of reputation and trust within the scientific community, that was important. If we look at Project Bates, that was a huge problem. The project, I'm not sure how many people were involved in the project, but it would be maybe 150. If the VAX 780 was down, then that's people sitting there twiddling their thumbs, not able to do their work. So continuity of service was critical. And again, I mean, what level of service you get from DEC depends on what service level agreement you've signed up to. But certainly, I was always impressed by the level of support. We were never left sitting around long. If we had a failure, there would be an engineer dispatched when we needed them.
And you mentioned a few things that are interesting there. So you felt like you were a sense of, a partner, a part of a family, almost a partnership with DEC in this sense?
Yeah, definitely. I didn't have the closest relationship because procurement and so forth would probably be talking on a completely different level, but certainly from the engineering point of view. And as I say, I used to welcome the visits when we used to get the engineers in, because I'd learned so much more from them.
You mentioned there on DECnet, for example, and you said how DEC was almost I think you talked about some systems had vendor-specific features. You had to relearn. You had to get into a different mindset with them. Obviously, DEC wasn't exactly an open systems company. It's just you happen to like their particular proprietariness. And obviously that's different to where we are today. Were you aware of that? Obviously you must have been aware. You were entering DEC's world. It wasn't an entirely open architecture, was it? How was that okay? Did that workable for you?
It was because for where I was working, DEC was everywhere. Okay, we used the GC 4085, and we did offline processing with Rutherford Laboratories with their IBM 360s. I mean, it was, yes. I mean, to an extent, you're right. You're working within a sort of bubble, but it just worked. It was just a nice space to be. When I sort of moved on in my career and sort of distanced myself from DEC, not voluntarily, it was just the way the career went. In a way, the world sort of felt like it shrank. A little bit of Sun Microsystems and Unix, and mostly Microsoft Windows. And let's face it, I mean, you're in a different world with the likes of Windows, because you are incredibly divorced from the supplier. Whereas, again, it goes back to the more tactile nature of when you're into the bigger systems such as mini computers, you are sort of more closely bound and more reliant day to day with those organisations.
And you talk about the support relationship. Obviously, support is there, software is downloaded these days. Do you think support relationships are different, quantifiably different with companies then versus DEC?
Well, I mean, yes, there are differences. One of the biggest things you would probably point out is that in the days of PDP-11s and VAXs, you tended to sort of rely mostly on the operating system and maybe one or two compilers. There was very little else that you would sort of layer on top of that, because that was the nature of the job you were doing. If you look at a typical sort of Windows installation, if I think about the sort of products on my desktop, there's Teams. I've got to have Zoom, because some of my contacts rely on that. You've got the antivirus software. You've got crikey, what else have we got on there? You've got the VPN. There's so many more things that I need. Then there's the applications. I currently work in SAS and Oracle, so I've got Oracle front ends, I've got SAS front ends. Browsers are now used to access a lot of software as a service and so forth. It's a completely different environment. I think we were sort of working with fewer products in those days. Another interesting thing I would say about DEC and its software is that if you actually look around and look at the fact that an awful lot of platforms that we were familiar with, Primes, DataGen, Harris, what have you, not only have they gone, but does anybody use their operating systems anymore? Digital equipment is not around anymore, but there's still plenty of people using OpenVMS, which evolved from VMS, and I've even managed to get it running on a Raspberry Pi. So it's still very much with us.
What do you mentioned the clustering as well, which obviously you correctly pointed to as the kind of the forerunner of computing to cloud computing today. Why was clustering important to you? What did it enable you to achieve wherever it was you were working at the time?
Well, the problem was that we had these data acquisition systems. So we had the measuring tables with the BEPS bubble chamber. We had another PDP-11 with the holographic bubble chamber. We had SweepNIC with another PDP-11. All sorts of things going on. But the problem was that you had to get the data from A to B. The final destination of the data would have been the Rutherford Appleton laboratory, and that all went via the GEC 4085. How do you get the data from those PDP-11s onto the GEC? And the answer to that question was you had to go into the computer room, and on each of the machines you had to load a magnetic tape. You had to write the data, then you had to take those 3 tapes downstairs and load them onto the GEC one at a time, and then transfer them. And immediately we could sort of do all of that at one command, and we could move that data around. That was probably the biggest thing that it gave us. I mean, we look at cloud technology today, and it gives you resilience and so forth. Early days with DECnet, I mean, it was the foundations of computer clusters, but it did allow you to do things like backup more effectively. So with standalone machines, the backup process was quite painful because you'd actually have to create a backup copy to magnetic tape on 3 different machines, store and manage those tapes and so forth. What we could actually do with clustering is you can back up those machines all to the bigger central machine, and then you only need to back up that central machine. The backup process for one of our PDP-11s is really quite painful because it only had one disk, and that was your system disk. And if you wanted to create another copy of the disk, then actually trying to do that was you ended up juggling disks in and out, and you had to be very careful because it had been. I did it once myself, backing up the old disk onto the new disk. It was so easy to do because you were juggling disks all the time. Just made it so easy. It was just move everything onto one machine.
And you described the DECnet project as one of your most abiding memories, I think.
I think because it was such a big step change. The ways of working. I mean, if you just step back and look day to day, we had 3 PDP-11s, we had a VAX 750, we had a JEC 4085. From my desk, I've got one terminal. Now today, you'd sort of be able to switch between those machines very simply. In those days, to actually move from working on the VAX to one of the PDP-11s, I used to have to get up from my desk, walk across the room, unplug a patch cord, and plug it into another socket in the wall to reconnect my terminal to another machine. All of a sudden, you could do all of that. You could work on all of these machines from one desktop. The fact that you didn't have to run around, you really felt that all of a sudden something exciting had happened. And
you rolled out DECnet as well.
Yeah,
how was that
not solely by myself.
Yeah.
I mean, it was the head of the computing did a lot of the work, but I was there. It was challenging. It was an old building.
What did you have to do?
Well, it was a case of getting the wire routed through the cable, through the roof spaces. Not all of the machines are on the same floor, so it had to take into account the ducting. Tapping the wire was nerve-wracking. There was obviously what they call sysgen, which is the system install, configuring the system. And I remember the first day that I was on one machine and able to connect to another machine. It was like a wow moment.
How much would you say is the forerunner of Ethernet?
Well, it was a form of Ethernet. It's just a proprietary protocol, not TCP/IP or what we use today. But it was Ethernet. The same principles. The machines try to commandeer that one line. Collision detection. If another computer's already got it, it tries again later. It's Ethernet. It's just that they chose a proprietary solution. Not sure what happened with DECnet longer term, but I guess they must have either made bridges so they could work interoperably, or maybe they did support TCP long term. But unfortunately, that would have been after my time.
So obviously you've got a lot of love and affection for DEC systems. You've used them quite extensively. Can you think of one particular system or workload that is your favourite? You look back. I mean, you mentioned DECnet obviously, but a favourite workload or application you pull out from history, or?
I think of all of them, I would pick out the holographic bubble chamber. That was really quite exciting. One of my key jobs there was to build a processing system that would allow review and editing of measurements, so to be able to read in the data and then to drive the stages to the positions. And I had to do some quite clever things with that, because one of the problems was, if you're in imagine you're looking at a tree, and you've got branches, and that's might be what a collision might look like, and when you're measuring, you've only got a simple display. We didn't have graphics on those machines, so if you were editing, you needed to know exactly where in the sort of tree of measurements where you were. So imagine looking at a tree and picking one particular branch, knowing that you're at that branch. And I suddenly realised that some work that I'd done parsing mathematical expressions could actually be sort of turned on its head, and I could use the same sort of nomenclature to replay at the bottom of the screen the structure by representation with brackets and arithmetic signs. And actually it turned out to be exceedingly successful, and it did actually get me a mention in the in somebody's PhD thesis as a thank you for doing that, which was quite rewarding. But it was just really exciting, because I mean, it's not only the sort of like working with the computer. There's actually a physical device sitting next to it where you see things move in control to the buttons that you're pushing, and it used lasers and all sorts. So from a technology point of view, it ticked so many boxes. It was just such fun.
And did you? And you said that, and so because people today, obviously, their sense they interact with the computer using a GUI, a screen, and a mouse. Then you're using keys, and it's like command line. How are you?
Yeah, I mean, it just purely text terminal was all we had.
So even though you're dealing with graphical images, you're dealing with text terminal to kind of view it or work around it.
Well, you couldn't actually view as a graphic the measurements. The digitization was literally building a data structure. That in itself was quite clever, because with languages such as Pascal, C, you're used to using dynamic data structures and linking. With these systems, we were working in mostly Fortran 4. And of course, Fortran 4 is very limited, and it doesn't provide any sort of dynamic data structure. But some clever people in CERN had built a package which I think it was called Hydra, and this allowed did some clever things behind the scenes using common data constructs to effectively build a dynamic data structure. And so we used the Hydra package to actually build trees. So each interaction would be a new node, and if an interaction split off into two paths, then you'd have a node, and then you'd have two new nodes linked to that to represent the two paths. And that was basically just basically a data structure that you could then export, but there was no means to actually view digitally the image. That was starting to happen with the Large Electron Positron Collider. I remember the department invested in a Megatech graphic display terminal, and that's when it was with the sort of the era of the Large Electron Positron Collider and the later physics experiments that everything went to solid state rather than drift chambers and rather than bubble chambers and so forth. So you weren't sort of going through an intermediate stage of a photograph.
Okay. So just go back briefly. You mentioned something DEC was good at was the quality of the documentation that you received. How important was that, and what kind of documentation were you receiving from DEC?
Well, it was absolutely vital. So, for example, one of the first jobs that I undertook was the interface between the measuring tables and the PDP-11 computers I mentioned was a system called CAMAC, which was just basically modular electronic components that sat in a rack. And the driver that was written for the PDP-11 was only designed to use one CAMAC crate, but you could actually sort of chain CAMAC crates together and have multiple crates. And so one of the first jobs I had to do was to update the device driver to handle multiple crates. And without the documentation, how to write a device driver for PDP-11 under RSX 11M, I wouldn't have been able to do that without the documentation. it also, I was dipping into bits of PDP-11 that even my university experience hadn't exposed me to. So to some extent, there was an awful lot of self-learning, and the documentation was vital for that. And there were regular updates. Every time there was a new software release or a patch or whatever, it would come with a set of pages, and I can remember spending many a time going through the big lever arch files, removing pages and inserting the new pages.
So I was going to ask, what was the documentation? How did it come to you? Did you ask for it? Did you receive it? And was it like large documents, like fat binders? Was it A4 sheet?
It was a shelf load of fat binders in many volumes, and I think when the VAX 750 came, there was even more than the PDP-11, and they were all in big, huge lever arch files. And so, if you received a software update or a patch, then you'd literally have to find the relevant pages of the manual, open up the lever arch, and take the pages out and insert the new pages you've been provided. So, it not like today where they just send you a new PDF, because obviously with a number of patches you couldn't sort of keep replacing a whole shelf full of documentation.
Where did you keep all this doc? How much was it? Where did you keep it?
There's probably about 2 full bookcases of documentation sitting in the office.
And that came to you just voluntarily? Did you have to ask for it, or did
No,
it
came. I mean, it came with the software. You bought the software. You got the distribution. Say, for example, on magnetic tape, and in the box would also be a stack of manuals. And of course, not only just for the operating system, but if you had Fortran, there were the Fortran manuals, the Macro 11 for the assembly manuals, and automatically with any update came the new pages. So it was quite well organised from DEC's point of view.
And did you ever? There was this network of software from the DEC environment. Did you ever use any software other people had built for your project?
Did occasionally. I mean, there was quite a lot of exchange between the universities and things that were done at CERN. There was, I mentioned writing a file transfer using the terminal lines, but that eventually got replaced with Kermit, which I'm not sure quite where that came from, but it was sort of third party, potentially open source, or I'm not sure if that was proprietary. But yeah, I mean, there was always a healthy exchange, and in those days you didn't need to worry about viruses.
It was interesting also you didn't need to worry about intellectual property, because today we would have open source where there's a license to protect the IP. But back then, were you aware of the terms and conditions of using this software? Were there any terms and conditions on using it?
Well, yes. I mean, it was proprietary, but of course, not like today where if I've got a PC on my desk and you've got a game on it, your next door neighbour's probably got a PC, so there's opportunity to share. But who would you share the DEC software with? I mean, everything was licensed. They had licensed keys. Generally there wasn't that level of sharing. But if somebody wrote a piece of useful Fortran, then quite often that would be openly shared amongst the academic community. It's very different.
And did you, so that people were okay, did you, at what point do you then start moving away from the DEC systems? You mentioned several times how you become more removed from it. When do you think was the last time you actually were hands-on with DEC systems, and you'd moved to what by this point?
Well, I ended up working for a consultancy firm and looking after their VAXs, so initially a 780, but then moved down to a microVAX with DECnet and some VAX stations. I've left that company in about the year 2000, and since that date never touched another DEC system. I do miss them. There's an awful lot going on in the sort of retro computer community, building various simulators, and I do have 2 PDP-11 simulators. One of them's actually got replica front panel with the switches and lights. I've got a hobbyist license for Open VMS, and I do play with them from time to time. One of my hobbies is astronomy, and I've been involved in a network of meteor cameras. And one of the things we can do with the data is try reconstruct what we call the dark flight after a meteor. If there's anything left, and it's no longer seen as an ionizing trail, if something falls to Earth, you want to predict where it might land. And I was playing with writing some dark flight simulation, and I've been in the process of porting that to a PDP-11 simulator. Very interesting experience, because it goes back to what we were saying earlier about the differences between the old technology and the new. My software is very heavily based around arrays and holds a lot in memory. Can't do that on the PDP-11 because there isn't enough space. Runs a lot more slowly. You know, with the Windows, I've got an answer almost, split second after hitting the key. With the PDP-11 emulator, it's quite satisfying to see the flashing lights crunching through the numbers, and it takes minutes. You know, it's very, very different environment.
Why do you still do this? I mean, a lot of people kind of today, especially technology disposable, and people move on. iPhones come out so frequently that you end up with you forget it. But you've got PDP emulators going on, and you're working with OpenVMS still. Why do you? It's still tugging at your heartstrings, or intellectually satisfying? Or it's part of you?
It's tugging on my heartstrings. It is intellectually satisfying. It reminds me of why I love computers and why I've enjoyed what I've done for so long, which I think is really, really important. I suppose I could say, I'm now in my 60s. There is this sort of belief of a midlife crisis. Some people get Ferraris. I play with retro technology.
What do you think DEC's legacy is then? Of the company ceased to exist. Did you notice the changes at all, I should ask? Because obviously it went through a lot of changes. Did you notice that as a customer or a user? Well,
I mean, at the time that DEC disappeared, I think bought out by first Compaq and then HP, I was sort of no longer as hands-on with DEC as I had been in the past. I did notice its passing with great sadness, because I loved being part of sort of DEC's world. But it was, I mean, it happened partly because of the change that was going on with mini computers effectively disappearing, with the power of the desktop, the whole computer world was changing, just as it is now with the people moving to the cloud. It's sort of, so I think to some extent the fact that it disappeared was masked by the fact that the thing that killed it off was there and was the most sort of dominant sort of thing that people saw with computers, the desktop, the laptop. But its legacy, well, there's all sorts of things you can probably point to. Probably one of the most significant is clusters and clustering of computers. But I think it's also it's also affected the way we think, the way we work. I mean, in much the way that, for example, if you look at the history of Leo, a lot of what is done in terms of data, business analysis and systems analysis came out of that early pioneering. I think there's just so many ways in which the way we work, the way we think, was sort of pioneered by digital. I think it was one of the first things that I would say the start of computers being accessible, moving away from the big mainframes to a small office room that you could walk into with a computer sitting there, pick up a tape, put it on, do it yourself, rather than rely on computer operators and night shifts and things like that. I think I think it has had a strong impact on us, and it's not just me. Don't take my word for it. Look on the internet and just see how many people out there are still participating in that DEC world through simulators of PDP-11. There's soon to be a DEC System 10 simulator launched. That's going to be quite interesting. It's going to take up a lot of space in my study because it's got a bigger control panel. But as soon as it's out there, I'm going to be getting one. There's a lot of people still using OpenVMS in hobbyist roles, even in business role. So that, you know, that the fact that DEC has gone, but there's just so many people out there still have DEC in their hearts, just says a lot, I think.
Do you think, and the legacy of clustering, what is that today?
Well, the fact that, I mean, the way we use the cloud, resilience. If I look at sort of my role, I'm sort of got one foot in the legacy camp. So we've got servers sitting somewhere in an office, and where, you know, all the data sits on machines in our office. But with the new systems that we're building, they're out there in the cloud. They're split across regions. If one region goes down, the other takes its place. You know, it's completely different world. Even from the way in which you account for your costs, capital expenditure, operational expenditure, it's completely transformed.
And do you think that's down to clustering having an underlying effect on that?
I don't think you say that's solely down to DEC. I mean, other people were networking, Sun Microsystems and so forth. But I think that they got their products out there early. And you know, the concepts that were in those early systems. So, yeah, I'd say it had you know, they were doing things in their own way. It was proprietary, but I think an awful lot of things were learnt from that.
And its impact on you, obviously, you've had a huge. Your career has been shaped by it, hasn't it? And what would you say? And you feel very emotional about it now, I suspect. What was its legacy on you?
Interesting. I've really loved everything that I've done in computing, but I did go through quite a long low patch because I moved away from coding. I moved and went into sort of management consultancy type roles, and it was only when I had a sort of a redundancy opportunity that I sat down and thought about it. And I've actually, through what I do now, I've gone back to my roots, and I've done that voluntarily because I realised it's what I loved most. And you know, in this sort of middle period of my career, every sort of step forward, every bit of career progression took me further and further away from the technology and what I love. And lucky enough, I've been able to go back to doing what I love doing. I think back to my days, particularly with University College. I would say it's the best job I've ever had. I would say it's probably one of the best jobs anybody could ever have if you've got a love of science. I wished I was still doing that now. I regret leaving, but unfortunately, you know, we all have to face the hard realities that, you know, academic world is not, you know, in its day with the way house prices were going in London, I couldn't afford to keep doing that job. And I had to move away from it to be able to establish a good lifestyle. But I, to this day, wished I could have stayed longer in that role.
In that role with DEC, or just in that role?
In that role with DEC would have been nice, but I guess, you know, DEC didn't survive, and they're using other systems now to do similar jobs within the sort of electronic data acquisition sphere. But I look back on those days very fondly, and in all honesty, I would say to have had that opportunity is a huge privilege. I feel very privileged to have been part of University College, and I actually feel privileged to have been working with DEC. I've been very lucky in that respect, and you know, that passion has stayed with me. And I think a lot of people probably out there feel the same, because if I just look at the simulator community, working with replica PDP-11s, there's such a huge amount of interest out there, and it's just fascinating to see, you know, the chatter on the various forums, people wrestling with trying to get DEC networking between machines. They're all trying to use that technology. It's lovely.
Do you think it's moved into a maker kind of mindset? Are young people coming into it from you can see?
I think I'm seeing mostly people like myself. I think there is an explosion in the level of interest in retro computing, but to most people, retro computing means playing 8-bit video games on Ataris and things like that. there is, I think, with my generation, I think there is a strong interest to preserve, and I've collected a few bits and a few things of interest in my time, and at some time I'm going to have to let go of that, and what will I do with it? I would like to pass it on to something like the National Museum of Computing, if there's anything there of interest, or to schools, or to something, just to pass on that knowledge and preserve. I mean, I think for me personally it's very important when sitting down and looking at the computing technology we've got today, is understanding how we got there. There's still lessons in that for modern coders.